So we are in step 4, which is feature engineering. In that we are doing feature selection. So to do the feature selection, we have learned various statistical tests, which are z-test, t-test, and chi-square test, one way ANOVA f-test, and regression f-test. Now let's put everything in one place. So if you have your y, which is dependent variable, could be interval or ratio, or independent variable which is interval or ratio, then we can select the z-test. Basically choosing the significance test based on the level of measurement in statistical analysis. Okay, so if y is interval or ratio, and x is interval or ratio, you can select z-test. And if your y is interval or ratio and x is dichotomous, then we can choose independent samples t-test. And similarly, if y is dichotomous and x is also dichotomous, you can go for independent samples t-test. And for example, if you have both y and x nominal, or both y and x dichotomous, then you can go for the chi-square test of independence. If you want to put it in another way, if your x and y both are categorical variables, then for you have one option, that is chi-square test of independence. Then we have if your y is interval ratio and x is nominal, like your y variable is continuous or discrete numerical variable and x is nominal variable or maybe categorical variable, then we can go for one way ANOVA f test. And again, if y is dichotomous and x is also dichotomous, still you can use one way ANOVA f test. And the last option, if your y is interval and a ratio and x is interval and a ratio, in that case we can do regression. For example, this test is specifically for regression, to assess the overall significance of estimated regression. We can use a regression f test, and we have done a lot of examples with respect to this. So with this, we have covered the most important tests with respect to the data scientist, and we have explained and we have done enough examples in keeping the data scientist in mind. So now we will be looking into the one more test, which is Tukey's test. So far we have seen a z-test. The z-test is a statistical procedure used to test hypotheses about population means when the population standard deviation is known. It involves comparing a sample mean to a known population mean and calculating a test statistic based on the standard normal distribution. And the most important thing is the z-test is typically used for large sample sizes, whereas t-test involves comparing the means of two independent samples t-test, or the mean of one sample to a known value, that's one sample t-test. However, we will be using two sample t-test. Okay, then the most important thing with respect to t-test is the t-test is a statistical procedure used to test hypotheses about population means when the population standard deviation is unknown or when the sample size is small enough. Then we went to chi-square test. So the chi-square test is a statistical test used to assess the independence or association between two categorical variables, and it involves comparing the observed frequencies in a contingency table to the expected frequencies. The test statistic follows a chi-square distribution. Then ANOVA with f-test. So ANOVA is a statistical procedure used to compare the means of two or more groups. It assesses the variability between groups and within groups to determine if there are significant differences among the means. So ANOVA provides an f-test statistic to evaluate the significance of the observed differences. So in ANOVA, the F test compares the variances between the groups with the variances within groups. In regression analysis, the F test is used to assess the overall significance of the regression model. So with that, we have covered up Z test, T test, chi-square test, and F test. Now it's time to look into the last test, which is a Tukey's test. And we had a mention in ANOVA's F test regarding the Tukey's test. So what is a Tukey's HSD test? Tukey's test, also known as Tukey's honest significant difference test. Tukey's HSD test is a post hoc test performed after conducting an ANOVA to determine pairwise differences between group means. It helps identify which specific group means are significantly different from each other while controlling for the family wise error rate. And that's what is our Tukey test, and that's what we're gonna explore now in this video. So Tukey's HSD honestly significant difference test is a post hoc analysis that can be used following an ANOVA to determine which pairs of group means differ significantly from each other. So this test takes into account the multiple comparisons problem by controlling for the family wise error rate, which is the probability of making at least one type 1 error across all pairwise comparisons. So the HSD test calculates a critical value for the difference between means called the honestly significant difference. So the HSD test calculates a critical value for the difference between means called the honestly significant difference value. If the difference between two group means is greater than HSD value, then we can say with a certain level of confidence that the difference is statistically significant. I'm repeating this again. If the difference between two group means is greater than HSD value, then we can say that a certain level of confidence that the difference is statistically significant. The HSD value is calculated based on the number of groups being compared. So the total number of observations and the significance level is alpha chosen for the test. So the Tukey HSD test can be performed using the statmodels.stat.multicomp module in Python. So it requires the group means and the standard deviations as well as the total number of observations and the number of groups being compared. The test outputs a table of all the pairwise comparisons. The test output, the Tukey's HSD test outputs all the pairwise comparisons along with their corresponding p-values adjusted for multiple comparisons using Tukey-Kramer correction. So overall, a Tukey's HSD test is a powerful tool for identifying significant differences between group means after performing an ANOVA, and it helps to avoid the problems associated with multiple pairwise comparisons without compromising the overall alpha level. So let's look into the example now. So this is what so we have done the ANOVA for this data set, and these are the results. As per the results, temperature, humidity effect on temperature and humidity effect on dependent variable is significant. You can see that F statistic is large and probability p-values are smaller. Clear? Then there is an effect between the groups also, because that F statistic also larger and also their lesser p-value, lesser than 0.05. So but we need to confirm So we need to confirm this. How can we do that? The Tukey's HSD test is a post hoc analysis that can be used following an ANOVA to determine which pairs of group means differ significantly from each other. That's what we are going to do here. So statmodels.formula.api import OLS and SM both. So data has been loaded. So once the data, after the data has been loaded, then you have to fit into the model. So it's been fitted into the model. Now let's perform Tukey's HSD test. That's a honestly significant difference test for temperature first. We are doing for the temperature or the temperature with growth rate. Obviously growth rate is our dependent variable, so it will be doing temperature with growth rate and humidity with the growth rate. And first we'll perform Tukey's HSD test for temperature, and that results we can see here. And then second one, we'll perform Tukey's HSD test for humidity, and that's what we see. Tukey's results So first one with the temperature that you can see here. Group 1 in temperature, we have a group 1, a group 2, two groups were made. And even for the humidity, group 1, group 2. So group 1, high, low. And then let's directly look into the P. Okay, P adjusted is 0.0. P adjusted is 0.0. The HSD value is calculated based on the number of groups being compared. So the total number of observations and the significance level chosen for the test. So if the difference between two group means is greater than the HSD value. So this is the mean difference. And so Tukey's HSD, it's 0. Of course, our value is 0.05. if 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 this mean difference is greater than Tukey's HSD value, so you got the lower and then upper. If it is greater than this, then obviously you have to reject it. Okay, you have to reject the null hypothesis, and you can see that, you can say that there is an effect. There is an effect from this. So from the temperature, you got the group 1, group 2, so both are true, means you have to reject it. But when it comes here, you can see that the mean difference is no more greater than the upper limit. Upper limit, you see that? Its upper limit is 0.3752, and here the mean difference is not even greater than upper limit, and then it's not even greater than upper limit. Oh, this is 0.288, it's positive. So these are all lesser than, that's why reject. So for the humidity, we will be accepting, or we'll be confirming the null hypothesis. That means there is not much of effect on the dependent variable from the humidity, but there is a huge effect. We are confirming the effect from the temperature on dependent variable, which is growth rate. So here with this result, what is the result? What is the conclusion from the ANOVA? The conclusion from ANOVA is temperature and humidity. The effect of temperature and humidity on dependent variable growth rate is significant. That's it. That's it. But we just want to confirm that significance. Then I have gone for the Tukey's HSD test, which is honestly significant difference. Then what it is saying, there is a significant effect on the growth rate from the temperature, but there is no significant effect from the humidity on the temperature. Hence proved, one has been completely neglected, one has been completely ruled out, and then temperature is stayed with us. So that's how we leverage the Tukey's HSD test. So overall, Tukey's HSD test is a powerful tool for identifying significant differences between group means after performing an ANOVA, and it helps to avoid the problems associated with multiple pairwise comparisons without compromising the overall alpha level.